This lesson is an introduction to graphing parametric equations. Some of you may have some experience graphing parametric curves, maybe from a high school pre-calculus class or something like that, whereas others of you maybe have never seen this at all before, and that's okay. We're going to go through it as though you've never seen it. So for some of you, it may be review, and for some of you, it may be new. So when we graph parametric curves, X and Y are defined independently according to some other parameter, like usually we use t as our second parameter. So we have X as some function of t. T might represent time, or it might represent an angle, could represent any quantity. And so we calculate X and Y independently according to this other variable t. And so we'll start off with a couple examples of graphing a parametric equation, and then we're going to try to relate it to its Cartesian curve, which is the normal x and y functions. Okay, so here we have x is t plus 1 and y is t squared. So the easiest way to graph a parametric curve that you're not familiar with is to plot some points. And so instead of just having x and y values, we're going to have t is going to change, and it's going to, x and y are going to depend on what t is. And so we set up our table like this, and we may want to plug in, here it says t ranges from -2 to 3, so we're going to plug in -2, -1, 0, 1, 2, and 3. And so if we plug -2 in for this t, we get -1 for x. If we plug in -1, we get 0. If we plug in 0, we get 1. Plug in 1, we get 2. Plug in 2, we get 3. Plug in 3, we get 4. Then to get the y values, we're going to plug t in here. And so -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. And so now we're ready to sketch a graph of this. And so now we're just going to plot these as x and y points. So -1, 4 would be here. 0, 1 would be here. 1, 0. 2, 1. 3, 4. And 4, 9. And so our graph is this part of the parabola. So it doesn't keep going forever because it specifically says t only ranges from -2 to 3. So this looks like a parabola, and it actually is a parabola. It's just a normal parabola that has been shifted to the right one. And so if we think about the parabola y equals x squared, that would look like this. And that has been shifted to the right one. So the equation of this parabola in Cartesian coordinates would be f of x is equal to x minus 1 squared. It's been shifted to the right one. And then we would have to stipulate that x is in between -1 and 4. Those are the range of x values that we use. So that's what the equation would be using Cartesian equations instead of parametrics. Okay, we'll do the same thing in example B. Set up a table of values for t, x, and y. And this time it says t ranges from 0 to 6. So let's plug in values like 0, 1, 2, 3, 4, 5, and 6. When you plug in 0, cosine of 0 is 1, and then it says y is just equal to t, so that's going to be the same as the t value. So in fact, we can plug in, since y is equal to t, it's easy to go ahead and fill in our y values. It's always just the same as whatever the t value is. And then if if t is 1, cosine of pi over 2 is 0. At 2, we get 2 pi over 2, which is pi. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is 1. Cosine of 5 pi over 2 is 0. And cosine of 3 pi is -1. And so now we can plot our points on the graph. So our first point is 1, 0. That would be here. 0, 1 here. -1, 2. 0, 3. 1, 4. 0, 5. -1, 6. And so we can see this is just like a sinusoidal curve. This is actually a cosine graph. And one thing you'll notice about this is that using parametric equations allows us to graph things that are not functions. And so to write this in, we wouldn't be able to write this in Cartesian as f of x because it's not a function, but we would be able to say x is equal to cosine of pi y over 2. Since y is equal to t, we can just substitute y in place of t, and now we have this written as a Cartesian equation where y ranges from 0 up to 6, and so that would be our Cartesian equation. It is not a function, so that's why we can't write it as y equals. We can't write it as f of x equals. Another thing I should mention is that you can check your graphs. When you graph them, it's really important to be able to graph these parametric equations by hand, but you can also change your calculator mode to parametric mode and graph them there and see what they look like. So for example, if we go to mode on any of your TI 83 or 84 models, you can go down to, right now it's on function mode. I'm going to change that to parametric mode. So PAR stands for parametric equations. So I'm going to change that to parametric mode. And then notice now that when you go to y equals, it looks a lot different. We have x of t and y of t. So I'm going to clear those equations out and graph the one that we just did to test it and see how we did. So our x equation, it says, is, let's see, we should make sure we're also in radian mode, which we are. Okay. And so x is cosine of pi t divided by 2. And y is just t. And now we should set our window. Notice that the window also looks different. We're going to set our t values to go from 0 to 6, because that's what it said in the problem. And the t step, that doesn't really matter. We can take smaller steps than that, maybe 0.05 or something like that. Small steps are fine. And then for the range of x values, those look fine. And our range of y values, those look fine as well. So let's go ahead and graph it. And actually, we do need larger y values because our y values went up to 6. And so I'm going to change our y values to go from -2 up to 10 so we can see that better. And so there's the same graph that we just produced by hand. So you can always check your parametric graphs on your graphing calculator by putting it in parametric mode. Okay, I'd like you to go ahead and try example C. So set up a table, plug in common angles that you can calculate without a calculator in between 0 and 2 pi, and then plot your points. Okay, so to do this problem, I set up a table and picked some t-values. I didn't choose all the t-values, I just tried to pick a few of the common angles that we know how to work with using sine, cosine, using sine and cosine. So when we plug in 0, cosine of 0 is 1, so we get 4 times 1 is 4. Sine of 0 is 0. At pi over 6, cosine of pi over 6 is root 3 over 2, which is about 0.866. And then we're multiplying that by 4, so 0.86, we'll call it 0.9. And so, well, here, let's write it as, so we said root 3 over 2 times 4, that would be 2 root 3. We can approximate that as a decimal a little bit later. And then sine of pi over 6 is 1/2. And then at pi over 3, cosine of pi over 3 is 1/2, so we get 2. Sine of pi over 3 is root 3 over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Cosine of 2 pi over 3 is 1/2. And so we get, or negative 1/2, so we get negative 2. And sine of 2 pi over 3 is root 3 over 2. At 5 pi over 6, cosine is negative root 3 over 2. So we're going to get negative 2 root 3. And this is positive 1/2. At pi, we get cosine is negative 1, so we get negative 4. And at let's see, cosine sine of pi is 0, and then at 3 pi over 2, cosine is 0, and sine is negative 1, and then back at 2 pi again, we get 4, 0, just like we did at the starting point. And so we can plot those points and see what it looks like. So 4, 0 is our starting point. And then as decimals, 2 root 3, square root of 3 is about 1.7, so that's going to be about 3.4, 0.5. So 3.4.5 would be about right there. And then this is going to be about 2, 1.7 divided by 2 would be 0.86. Root 3 over 2 is about 0.866, so about let's just call it about 0.9. So 2.9, and then 0, 1, and then negative 2.9, and then negative 3.4, 1/2. That's this point. Negative 4, 0, 0, negative 1, and back to 4, 0. So we didn't fill in all the intermediate points down on the bottom, but basically we should be able to recognize that this is looking like a, sorry, I went to, this point was actually only right here. And so what we get is an ellipse. If you wanted to fill in more values in between, you could do that to see that we'd get matching points down here on the bottom as well, if you filled in more of the values. Okay, and so that is our graph for example C, and that is an ellipse, and you may or may not be familiar with the equations of an ellipse, but this would basically be x squared over 16, because this is 4, plus y squared over the vertical change is 1, so y squared over 1 equals 1. So that would be our Cartesian equation. If you haven't studied the equations of conic sections like parabolas and ellipses and hyperbolas and whatnot, then that would be that might not be one that you're familiar with. Okay, again, go ahead and pause your video and try example D. So this says that t could represent any positive value, and so I'm going to plug in numbers like 0. We're going to have to take the square root of these numbers, so I'm going to do 0, 1, numbers that are easy to take the square root of, like 4, 9, 16, and so on. And so this is going to be 0, 0. When x is 1, we get the square root of 1 is 1, so we get negative 1, 1. Square root of 4 is 2, so that's going to be negative 2. Y is the same as t, so that's 4. The square root of 9 is 3, so we get negative 3. Y is the same as t. And then negative 4, 16. And so we're going to have the point 0, 0, negative 1, 1, negative 2, 4, negative 3, 9, and then negative 4, 16. So our graph for this one is part of a parabola. It's just the left half of a parabola like this. You can kind of picture that the whole thing would look like this, but we only have the left half and only part of it going from x equals negative 4 to x equals 0. And so what we could do is to write the equation for this, if we substitute y in place of t, since y is equal to t, then we get x equals negative square root of y. And if you square both sides, you get x squared equals y. And so this is just the parabola y equals x squared, but we're using that from x equals negative 4 to 0. And so that's the Cartesian equation for this parametric curve. Okay, go ahead and try example E. Plug in values between 0 and pi, plot some points, and see what you get. Okay, plugging in all of these x values, these are common values that we know how to calculate sine and cosine for these angles. And so cosine of 0 is 1, so we get 4. Sine of 0 is 0. Cosine of pi over 6 is root 3 over 2, times 4 is 2 root 3. Sine of pi over 6 is 1/2, times 2 is 1. At pi over 4, we get root 2 over 2, so that's going to be 2 root 2. And sine of pi over 4 is root 2 over 2 also, times 2 would just be root 2. And then here we get cosine of pi over 3 is 1/2, so we get 2. Sine of pi over 3 is root 3 over 2, so we're just going to get root 3. At 1/2, cosine is 0. Sine is 1, so we get 2 times 1. At 2 pi over 3, cosine is negative 1/2, so we get negative 2. Sine is positive root 3 over 2, times 2 would be positive root 3. At 3 pi over 4, we get root 2 over 2, negative root 2 over 2, times 4 is negative 2 root 2. And then sine is going to be positive root 2. At 5 pi over 6, we get root 3 over 2 times 4, negative root 3 over 2 times 4, and that's going to be negative 2 root 3. And sine of 5 pi over 6 is 1/2, and that is 1. At pi, we get 4 times negative 1, negative 4, and we get 0. And so if we plot those points, 4, 0, 2 root 3 is about 3.4, because root 3 is about 1.7, so 3.41. And root 2 is about 1.4, so that's going to be 2.8. 2.8, 1.4. 2, 1.73. 0, 2. Negative 2, root 3, which is about 1.73. Negative 2 root 2 is about negative 2.8. And the y value is about 1.4. And then negative 3.4, 1. And negative 4, 0. And that's where it ends. So that is the top half of an ellipse. And since this minor semi-axis is 4, a equals 4, b equals 2. Again, this is an ellipse, but just half of it. And so it's x squared over a squared, which is 16, plus y squared over b squared, which is 4, equals 1. And we're only taking positive values for y, so for y greater than or equal to 0. So that's the Cartesian equation for that one. Okay, and then one more of these to try. Go ahead and pause your video and press play when you're ready to see the solution. Okay, if we plug in values like 0, 1, and 2, we get 0, 1, 4, 2, root 3, 0. And so if I plot those points, We have 0, 2, 1, 1.73, and 4, 0. Oh, my first one was 0, 2, not 2, 0. So that one belonged here, and then 4, 0. And so if I connect those in order, I get that, which looks like part of a parabola. Notice that we can do a substitution here again. Since x is equal to t squared, I can put x in place of that t squared to get the Cartesian equation. So then we have y equals the square root of 4 minus x, and because t squared got replaced by x. And so now if I square both sides, y squared equals 4 minus x. And so x equals negative y squared minus 4, or plus 4. And that is a sideways parabola. And let's see, x has to be in between, or actually y, since it's I wrote it as a function of y, we'd say y has to be in between 0 and 2. It's just the top half of the parabola. If you think about the parabola, that would look like this. We're just dealing with the top half of the parabola, and so y is in between 0 and 2. Okay, for our next example, we're going to see how we can use a parametric equation to write the equation of what we call a cycloid. And that's what happens when you have a circular object that is rotating around, and we're trying to keep track of the location of a point. So if you think of this as a wheel rolling along the ground, it would be turning this way as it rolls. And so how does the location of this point change over time? So you can, before we do this mathematically, try to predict what you think is going to happen if you drew out what is the path of point P going to look like. Now it's clear that point P is going to go up and down as this wheel turns, but as far as what its path looks like, that might not be as easy for you to see. Okay, so the way we're going to approach this using parametric equations is by realizing that this is just a point on it. We can think of it as a unit circle. The radius is actually 2, so it's not quite a unit circle, but we can use our unit circle values. And so as this point, so if we think of this as like a starting value, a starting point, and then we can say that the angle that it rotates through to get to point P, we're going to call that t. So that's our parameter t, is the angle. So let t equal the angle through which the wheel has turned. Okay, and then the arc length is going to be 2t, because circumference is 2 times the angle, and so whatever that angle t is, the arc length from there to there is going to be 2t. So that's how far the wheel has actually traveled. So the distance traveled horizontally is 2t, and that's also the arc length. Okay, so if that's how far the wheel has rolled, then this point would have moved horizontally that way. So we can say x is equal to, let's see, so x would equal 2t plus where it's located on the unit circle. So the center has moved by 2t, but even if the center was stationary, point P is rotating around and around and around this figure. And so the location on the wheel, the x position is the cosine. So that's going to be the cosine of the angle, negative t. The reason why I'm using negative t is because the wheel's turning clockwise, and we're usually in standard position for unit circle geometry. We always think of a positive angle as moving counterclockwise. So that's why I put a negative in front, because it's turning the opposite direction. And then the y position is just going to be the sine. So if you think of this is x and this is y, or the x, the the x position is moving because the wheel's moving horizontally, but it's also changing over time. And so the y is sine of negative t, but then it's shifted up 1 unit, and so, or up 1 radius length, so that's actually 2 units. So this is going to be 2 plus sine of negative t. And so those are the equations that should map out the point as the wheel moves along. So we can try this out on our graphing calculator and see how it looks. So I'll clear out what's there. And so if we do 2t plus cosine of negative t, and then y is going to be 2 plus sine of negative t. And then for our window, t starts at 0, and then it rotates through an angle of, well, we can go several rotations around. There's no limit to how far the wheel can go. And so let's go from 0 to maybe, let's see, 0 to, it's an angle. T is an angle in radians. So we can go to maybe 10 pi. So that would be 5 rotations around the circle. And let's see, that's fine. X, then it could travel quite far, so we should go from maybe negative 4 up to positive 30. Let's see if it reaches that far. And then the y value is staying, of the center is staying at 2, so we could go from negative 2 up to 5. Okay, and now let's graph it and see how we did. Okay, so something's not right with that graph because the wheel should be, the point P should touch the ground sometimes, so it should be at a height of 0. So let's see. Let me see what I typed in here. Oh, we should have 2's in front of both of these because the radius of the circle is 2. And so if I fix that, if I put a 2 in front of the cosine and a 2 in front of the sine, and now graph it. There we go. So that is called a cycloid, and that is the path that point P will follow as the wheel rolls along the ground. And it keeps going. For the next couple examples, we're going to look at a graph and then try to decide what would the parametric curve be that meets the description. And so if we picture, for this first one, we have a line segment that goes from -1, 3 to 3, -2. So just a plain old line segment, but how would you describe that parametrically? So one thing that's interesting about these types of problems is there are really infinitely many solutions, and it just all depends on how we want to describe our t-values. So one way to set this up is to just simply say x is t, and then when we read our equation of the line, y is just going to be a function of t instead of x. And so the slope is 1, 2, 3, 4, 5 over 1, 2, 3, 4. So our slope is -5/4. And so you could just say y is equal to -5/4 t plus the y-intercept, which it's not real clear what that y-intercept is. So we would say y equals -5/4 x plus b, and then plug in a point like -1, 3. So 3 equals -5/4 of -1 plus b. And so then b would be, this is 12/4 plus 5/4, or actually -5/4. And so that would be 7/4. And so our equation is y equals -5/4 x plus 7/4. So that's just writing the equation of a line like you did many years ago back in algebra. So here, now we're just saying since x is t, we can replace the x's with t's and get -5/4 t plus 7/4. Okay, so that's one way to write the parametric equation. And since it has endpoints, we would want to specify that x has to be in between -1 and 3. So those are the parametric equations that would create that graph. Again, you can graph that on a graphing calculator in parametric mode and see that that actually would be the same. Okay, let me show you another option, and that is, a lot of times the solutions you'll look at in the book, they want the initial point to correspond to t equals 0 and the ending point to correspond to t equals 1. And so we can accomplish that. So let's think of the point as being 0 for t, -1 for x, and 3 for y. And then we'll think of this point as being 1 for t, 3 for x, -2 for y. And so if we just want the relationship between x and t, we can say x is starting at -1, and then there's some multiplier to get some multiplier of t, because it is a line, so it can fit a linear equation. And so if I plug in, and notice that when t is 0, that's just going to give us x equals -1. Now when t is 1, we want x to be 3. So 3 equals -1 plus a times, we said when t is 1, and so that means a has to equal 4. And so our x equation is x of t is equal to -1 plus 4t. And then we can do the same thing with y. Y is equal to the starting y value plus some multiplier times b. And when b is, when y is -2, we want t to be 1. And so then we get -5, b equals -5. And so our y equation is going to be 3 minus 5t. And notice, so and this is for t values in between 0 and 1. So 0 corresponds to the starting endpoint, 1 corresponds to the other endpoint. And so here's two different sets of parametric equations that create the same graph. But one thing that's interesting is these numbers that are in front of t, those match the slope, because 4 is the change in x and -5 is the change in y. And so that will generally be the case if you're just writing the equation of a line segment using parametric equations. Okay, this time we're going to see if we can write the equation for the left half of a parabola. So if I factor this out, this would be x times x plus 2. So this is a parabola that intersects the x-axis at 0 and -2. So 0 and -2. So that would be a parabola that looks something like this. And so again, there are a couple of ways we can write the equation of this. It says just the left half. And so that would just be that part of the parabola. Notice that we don't really even know what this low point is. We'd have to plug in -1. So if we plug in -1, that will give us the point. And so -1 squared is 1. And then this would be -2. So we get -1. So it actually goes through this point. So that is the left half of the parabola that we're trying to graph. And so to do that parametrically, you could say x of t equals t, y of t is equal to t squared plus 2t. So that would be the easy way out. And then we would have to say, since x is t, we'd have to say t is anything less than, since this is x values less than or equal to -1, then t would have to be less than or equal to -1. Now that's fine, that works. But it's kind of weird to have t values that are getting smaller and smaller going on forever. Usually we want to have a starting point for t and then let it increase. And so another way to write the equation of this would be to, since this is shifted left 1, we could say x is equal to t minus 1. And then since we know that y is equal to x squared plus 2x, we could say that that is t plus 1, or sorry, t minus 1 squared plus 2 times t minus 1. And if you expand that out, you get t squared minus 2t plus 1. Here we get minus or plus 2t minus 2. And so altogether we get t squared, the 2t's cancel, and so we get t squared minus 1. And so this would allow us to say that if we use these parametric equations, x of t is equal to t minus 1 and y of t is equal to t squared minus 1, then we would have t is anything less than 0. So at least in this solution, it starts with t equals 0, but it's still going down. It's going backward. So you could replace all the t's with -t, and then you'd have t could be greater than or equal to 0. So then this would be x of t is equal to -t minus 1, and y of t is equal to, since it's -t, when we square it, it's still going to be t squared minus 1. And so we could try this one out on the graphing calculator and show that it produces the correct graph that we're looking for. And so if we put in y equals t minus 1, actually we said negative t minus 1, negative t minus 1, and then this one is going to be t squared minus 1. And for our window, we said that t has to start at 0 and can be anything greater than 0. So we'll say 0 to 100. It doesn't really matter. Okay, 0 to anything big, it's going to go off the screen. Our t step, let's do 0.1 since that's a long way to go. And then x, from the graph that we see here, our x values are only negative. And so we can go from like negative 10 to 2. So that's mostly negative numbers. And then our y values go from, we want to go from at least negative 2 up to 5. That should work, or we could even go higher and go negative 2 to up to 10. Okay, so now if we graph, we'll see what it looks like, and that does look very good. It starts at the point negative 1, negative 1, and it goes upward forever to the left. So that does look like the correct graph. So here we came up with 3 different solutions that work. This one starts with t equals 0 and then increases from there, whereas these other two have decreasing t values in order to produce the graph. So all of them are fine. It's just good to understand. Sometimes when you read a solution in the textbook, this is usually what they're going to do. They're going to try to start with t equals 0 and then let t increase to produce the rest of the graph. So here I've picked out some good practice problems, especially the odd numbered ones. You'll be able to check your answer and see if you're doing them right. Let me know if you need any help, and have a great day.